Okay. So for our only class this week, well, look at the two lessons that are pretty closely related. And honestly, you think of these two lessons, they're kind of review in a way. Because it deals with separation of variables and also eigenfunction expansions, which we saw with non-homogeneous PDEs, and how it relates to the various Fourier transforms that we've seen for problems, or really finite Fourier transforms for problems on a bounded interval, where we have boundary conditions at both endpoints. But the main new thing that comes out of today's lessons is how you can take take an initial boundary value problem, especially one that has a non-homogeneous PDE, and break it down into simpler problems. Because if you have problems that have multiple complexities, such as non-zero initial data, a source term, etc., you can break them down into a handful of problems that only have one of those complexities to deal with at a time. And you can solve those problems independently and add solutions together when the PDE is linear, which is what we'll see in today's cases. So we're exploiting that linearity to cut a problem down to size. All right. Now, so when we're dealing with a PDE on a bounded interval, like 0 to L, we've seen how we can use separation of variables to solve it. And we can also use a finite Fourier transform. Now, we have seen these finite Fourier transforms before, but you'll recognize a similarity between this approach and also using separation of variables. You can see that really there are two different perspectives on the same solution technique. So for completeness, here we have a definition of a finite sine transform, where you're integrating your function f and your little f and you're transforming times sine n pi x over L on the interval 0 to L. And then we have a scaling factor of 2 over L. And applied to a function f of x, we denote the transform by capital S of f in square brackets. That refers to the sine transform of f. But what is a sine transform of f? It is a discrete set of coefficients, s1, s2, etc., sn. So the input is a function of x, the output is a sequence of coefficients. But it can go the other way. If you have the sequence of coefficients, Sn, you can take the inverse sine transform. And that amounts to taking a linear combination of these basis functions, sine n pi x over L, where the coefficients are the Sn. And that's used to recover the function f of x you're transforming in the first place. So S inverse of S of f brings you back to f. Now, this is transform, and we've seen this before, transform that should be used if you have Dirichlet, also referred to as type 1 boundary conditions, where the value of the solution is specified at the endpoints. And that's just because sine n pi x over L satisfies those same boundary conditions. If you plug in x equals 0 or x equals L, you'll get 0. On the other hand, if you have type 3 or Neumann boundary conditions, where the value of du dx is specified at the endpoints, then you should use the finite cosine transform, which has a nearly identical appearance. So the transform itself, you're just using cosine instead of sine. Everything else is exactly the same. But you're also computing coefficient C0. So you find the difference between the values of little n here. So 0, 1, 2, etc. for cosine, and 1, 2, 3, etc. for sine. That's because cosine n pi x over L is non-zero when n is 0. Here's the inverse transform. Same kind of infinite series with cosine instead of sine. But don't forget the constant term, C0 over 2. The over 2 is just so we can have one formula for all of the cosine transform coefficients, including C0. What some books will do is not have a 1/2 factor, and then C0 will be a special case where it's 1 over L instead of 2 over L. So it's helpful to be aware of that, these different conventions. I mean, I feel like you could pick up 10 different sources and see 10 different ways of describing Fourier transforms. Maybe not that many differences, but there are several of them. Kind of like how, when you took trigonometry and you dealt with quadrants, and there was universal agreement that how the quadrants were labeled 1, 2, 3, and 4. So they ask you, ask anybody, what's the second quadrant, third quadrant, and no points for right one. Now, in 3 dimensions, the 3-dimensional space can be divided into 8 octants, depending on whether x, y, or z is positive or negative. And while there's, again, universal agreement about what is the first octant, where x, y, and z are all positive, there's not agreement on the rest, so we don't bother. You just never know how people are going to order the octants, so it's not really discussed. Okay. So either one of these transforms, if you have a PDE in x and t, you apply the appropriate Fourier transform, the spatial variable, and the result is an ODE in t. But the ODE has the index n as a parameter, so really a PDE is transformed into a one-parameter family of ODEs, and we've seen that before. Now that's for one space dimension. If you have multiple space dimensions, you have PDE, like say x, y, z, and t. You can apply Fourier transform in each spatial dimension. So integrals with respect to x, y, and z to deal with partial derivatives with respect to those variables, and again you have an ODE in t. Now, to set up an example that I'll do a little later, this is one of our early homework problems, I believe. When we first started doing the Fourier transforms. If you have a function f(x) equals 1 on 0 to 1, then you would get the finite sine transform. So you put our function 1 in here, and then the formula calls for multiplying the integral by 2 over L, but L is 1 in this case. So you go ahead and work out the integral, and when you plug in the limits, cosine n pi x is equal to 1 if n is even, and minus 1 if n is odd. So if you consider the cases of n even or odd separately, then this is what you get. So we only have non-zero coefficients when n is odd. You may remember this homework problem. So now, if I want to take the inverse sine transform of these coefficients, if I just use the definition, so I'll fill that in first, you would have a sum equals 1 to infinity of Sn sine n pi x. Okay, yeah. So that's what the definition of inverse sine transform would give you in the case of L equals 1. Now, to properly take into account the fact that Sn is 0 when n is even, we want to write this sum in a way to consider only odd values of n. So, if we write the sum this way, n going from 1 to infinity, then 2n minus 1 would give us odd integers. So, for n equals 1, 2, 3, etc., 2n minus 1 would give you the odd integers, odd positive integers that we want. 1, 3, 5, 7, etc. So then 4 over pi times 1 over an odd integer, that accounts for this coefficient. And then we're multiplying by sine n pi x, but only for odd values of n. So, so that would give you this sum, where only odd multiples of pi x are considered here. 1 over odd integers is given here. And then the 4 over pi has been factored out just because we can do that. Equivalently, you can use 2n plus 1, which is also odd, as long as you start at n equals 0. So 2n plus 1 starting at n equals 0 is equivalent to 2n minus 1 starting at n equals 1. I want to show you both of these because I've seen answers in either form, like in the homework, and they're correct as long as you make sure to start n in the right place, so that the proper integers are covered by your summation. I should mention a way to readily derive this summation from this one is the following. If I want to write this sum in such a way that the index starts at 0 rather than 1. So this is something you can do summations in general. And actually, this is something that will come up a number of times in the class I'll be teaching in the fall, Math 415, which I know both of you in this room are taking. So I'll be sure to remind you of this end. How to manipulate summations to get them in the form that you need. If I want to start this at n equals 0, okay, so I decrease the starting index by 1. Then I need to replace n by n plus 1 throughout this expression. So if I do that, and do it carefully by watching my parentheses, this is what you would get. So this is useful in many situations outside of PDEs. It's one of those general good to know things about how to manipulate these kind of expressions. Okay. And so all we're seeing here is the inverse transform of the sine transform of 1, which brings us back to 1. But I should point out, because the function 1 does not satisfy the boundary conditions, the boundary conditions call for being equal to 0 at the endpoints 0 and 1. And because this function does not satisfy that, that means you're not going to get convergence to 1 at the endpoints. In the interior of the interval, you do. Although as you get closer to the endpoints, that convergence may be slow. And I think I showed a MATLAB demonstration of it some time ago. That you get funky behavior near the boundary. So that's something to keep in mind. When the problem data is not compatible. Like you might have incompatibility between the initial conditions and the boundary conditions. Now, the way we use finite Fourier transforms, sine or cosine, to solve PDEs, we transform the PDE itself. We take the transform of the initial condition. We select the transform we want based on the boundary conditions. Here are the rules for transforming derivatives. So in the case of derivative with respect to time, well, we're applying the transform in x. So Fourier transforms and derivatives with respect to time can be applied interchangeably. Another way of putting it is the transform of the time derivative is the time derivative of the transform. That gives you these four rules here. The first and second derivative with respect to time, either cosine or sine transform. So that's the easy part. There's a different story for derivative with respect to x. Now, if you take the second derivative of cosine or sine n pi x over L, what you will get is that function itself times the scaling factor minus the quantity n pi over L squared. So derivative of the transform of the second derivative is this scaling factor times the transform of the original, but you must include these boundary terms. And if you were to take use the definition of the cosine or sine transform applied to uxx, you can figure out what it is by using integration by parts twice. The boundary terms that you get along the way give you these boundary terms here. You know what? I'm going to do one of these. I put a sine transform. So sine of uxx. So that's going to be, by the definition, that'd be 2 over L times the integral from 0 to L of uxx xt times sine n pi x over L. I'm going to take a second to make sure I want to make sure my equations are formatted in the same way. Okay, using parentheses. Let's do the unambiguous there. Okay. So that's just what the definition gives us, but now I can use integration by parts where sine n pi x over L is the u, and uxx dx is the dv. So for the u part, we'll have sine n pi x over L. And then for the v, I integrate the dv, and I get ux. And then going to evaluate that at the limit 0 and L. And then I'll have Oh, I don't want to forget my scaling factor, 2 over L. And then I'll have minus the integral of v du. So I'm still going to have my factor of 2 over L. And then integral 2 over L. Right. So I'm going to have v, which is ux, du. So the derivative of sine n pi x over L will give me cosine but times n pi over L. So I need to include that here. Okay. Now, what happens when I plug the limits 0 and L in here for boundary terms? What am I going to get? Anyone?
1 and, well, just 1. No, 0.
0, yeah. Yeah, I plug in x equals 0, I'll get sine of 0, which is 0. If I plug in x equals L, I'll get sine of n pi, where n is an integer. That's also 0. So these go away entirely. That helps. Now, as for this, I'm going to apply integration by parts the second time, where this ux dx will be the dv, and cosine n pi x over L, that will be the u. And I can't forget the scaling factor out here. So now I'm going to have minus 2n pi over L squared. All right, so I'm going to have v, which is going to be u, and then the u part of for integration by parts formula is going to be this, cosine n pi x over L. With limits 0 and L. Okay. All right. And then I have still the integral of v du, a minus, but then that's going to give me a plus. I over L squared, integral of v du. So the v part is going to be u of xt. And then I'm going to have the derivative of this. So the derivative of cosine will be minus sine. So that's going to give me a sine here. And then I have to multiply by n pi over L. And then I'm going to have a minus. So now I'm going to have minus n pi over L. So I'm going to have n squared pi squared I feel like something's amiss here. Okay. have minus, the division of partial limit gives me plus. Okay, this part we're gonna have. Alright, this part is going to work out correctly, no issue there. Different part's fine too. This is what I get for doing something improvised or unplanned. I'm going to write this fraction as two fractions, 2 over L, then n pi n squared pi squared over L squared, but that's the same as n pi over L, the whole thing squared. Okay. Oh, okay. Now, and then I'm going to put the minus 2 over L. No, just 2 over L. Right next to the integral. Okay. Now, what we have here, that is the definition of a finite sine transform. And that's multiplied by minus n pi over L quantity squared. So I'm going to put this in brackets. This is easier to see. Okay. All right. Now, when I substitute x equal L and x equals 0 in here for limits, okay, so I'm going to copy all of this. All right, so part of is large square brackets here. That's just capital S of U, the finite time transform. And then for the rest of it, we have two boundary terms, x equals 0 and x equals L. So here I'll substitute x equals 0, or sorry, x equals L first. So that's just going to be cosine of n pi. And then u of LT. And then over here I have u of 0t, cosine of 0, but that's just 1. And then lower limit, I need to put a plus here. So then cosine of n pi, that's minus 1 to the n. So let's fill that in here. And then I have 2n pi over L squared is a common factor, so let's pull that out. And then here I have minus and minus 1 to the n. But I can put those together, and that'll give me minus 1 to the n plus 1. And you see that the formula that we've arrived at is exactly this. So any questions about that? And then it would work out similarly for cosine, again doing integration by parts twice. For the first time around, the boundary terms would be non-zero. The second time around, it would be 0. So now I'll show you how you go about using a finite Fourier transform, sine and cosine, in solving an Ibdp. So as an example, here's our problem. And so we have a source term, so the PDE is non-homogeneous. We have a homogeneous Dirichlet or type 1 boundary conditions. And then this is a wave equation. So the ideas we're talking about here can be applied to the heat or wave equation. So here are two initial conditions. I need to introduce some notation a little earlier than I have in these notes. So our solution U as a finite Fourier sine transform, and I'll use so that's going to be a discrete set of coefficients, and I'll use capital Sn to refer to that. Then we can say from the inverse sine transform, that's a formula for it. We have the following: U of xt is a sum from 1 to infinity Sn sine n pi x. N pi x over L, but we see that L equals 1 in this case. So here we have the form of our solution. But I should mention Sn is a function of t, just because U is a function of x and t. All right. So, knowing our solution is this form, these are what we need to solve for. Now, first we can figure out what are the initial values. We get that by taking the transform of the initial conditions. So we have to take the finite sine transform of function 1 that I showed you earlier. That's given here. Then the other initial condition is 0, so that's what the other initial value would be. Now, because the PDEs in x and t, once we apply the finite sine transform to this whole problem, we're going to have a family of ODEs in t. So we need to get that. So here we use our transform rules for the derivatives that we have in our PDE. The UTT, which just gives us a second derivative of our transform of our solution. And then for UXX, we have a rule that I derived earlier. In this case, the boundary values are both 0. So we're not going to have this part at all. It's just going to be this. So those two rules will help us with transforming the PDE as a whole. So if we look back at the PDE, so this time we're going to have Sn double prime of t. Here we're going to have minus n pi squared times Sn. Then we also have a source term to deal with. That's going to add an extra term. So the finite transform of sine pi x, this is our source term. And this is what we get from the definition of a finite sine transform. But that's just only going to give us 0 unless n equals 1, in which case you'll get 1. So just from working out the integral directly. So now, the transform of a PDE can be completed. So here's our PDE, repeated. So for time derivative, we get S1 double prime. For UTT, for UXX, we get minus pi squared S1. This first line is just for n equals 1 case. So from a source term, sine pi x, in an n equals 1 case, we're going to get an extra term of 1. And for all other values of n, we'll still have this part, minus n pi squared as n. But the source term will not contribute anything because the source term does not have any non-zero coefficient for most values of n. So here's our one parameter family of ODEs. We just have a special case of n equals 1. Now, because the ODE in this case is non-homogeneous, you can use methods that are taught in the first ODE course, like F 285, such as undetermined coefficients or variation of parameters. From using a method of undetermined coefficients, it can be found that the general form of solution is this. So it's a linear combination of cosine pi t, sine pi t, and a constant function. we just have to figure out what the constants are that satisfy the PDE, and also the initial conditions. And here are the initial conditions for the n equals 1 case only. Well, for all values of n, the derivative, Sn prime is 0. And then for S1, we get 4 over pi. And that comes from this transform of the initial data. So we're just using this in the n equals 1 case. Okay, for initial values. Okay. So now we go ahead and substitute this form into this ODE and these initial conditions. So between the ODE and the initial conditions, those are 3 constraints on the 3 unknown coefficients, A, B, and C. That allows us to solve for A, B, and C uniquely, and this is what we get. So that's S1 of t. For all other values of n, the ODE is homogeneous, so that's easier to solve. Now, for a case of n even, we have a homogeneous ODE, and for n even, both initial values are 0. That means the whole solution is going to be 0. So that leads us to Sn of t being 0 when n is even. When n is odd and greater than 1, here we have a non-zero initial value, so solving that second order homogeneous ODE that gives us this. So now we have Sn of t defined for all positive integers n. So here's S1, here's Sn for odd numbers, and then even numbers. So now we take the inverse sine transform. So S1 of t times sine pi x. And then we have the other coefficient, the other coefficients. So 4 over n pi times cosine n pi t, only for n odd, times sine n pi x, where again n is odd. So in other words, this is what you get from taking the form of the solution given earlier, this form, and substituting the solutions of our one parameter family of ODEs in there for Sn of t. And then we're done. So, as we see in other problems, you transform a PDE, you transform the initial conditions, you transform the source term, if there is one. The result is a one-parameter family of ODEs. Now, if you're solving something like a heat equation that's first-order derivative in time, it's a first-order ODE with one initial value. If it's something like a wave equation, it's a second-order ODE with 2 initial values, because you have 2 initial conditions. So whatever kind of initial value problem you have for these was one parameter family of ODEs, you go ahead and solve that by whatever techniques, again, that's 25 type techniques. Then that gives you the finite Fourier transform of the solution. You then apply the appropriate inverse finite Fourier transform, and you have your solution u of xt. So, this is, we'll write that down here. All right, so what you do is, to PDE, initial conditions, source term, one parameter family of ODEs. Inverse, whatever transform we took at the beginning, take the inverse corresponding inverse transform at the end. Get u of xt. It's a one parameter family of ODEs for a problem in one space dimension. Here we have u of xt. If it was in higher space dimensions, then we, like say there's 3 dimensions, you have a solution depending on x, y, z, and t. Then you have a 3 parameter family of ODEs to solve. So questions about how that examples work? All right, as I mentioned, you have a linear problem that can be broken down into simpler problems. Here's one example of how you might do that. As an example, we have a heat equation problem with a source term, so PDE is non-homogeneous. We have homogeneous Dirichlet boundary conditions. And then here we have our initial condition that's non-zero. So what you can do is break that problem down into problems that have only one of these features at a time. Like this problem right here, you can see it's the same except for the initial data, it's 0. We keep the source term. So now you have a non-homogeneous PDE, homogeneous boundary conditions, and initial conditions. Which would mean that when you go to solve your ODEs, resulting from your Fourier transform, those will be simpler. And then the other problem has no source term, but it does have initial data. So all of the ODEs that you'll be solving are homogeneous. So you get the different implications in different problems. And then you solve these, and you can think of this, the original problem, as being the sum of these two. Because you add the PDEs together, you get the original PDEs, and similar to the initial conditions and boundary conditions. So the solution of the first piece is this right here. And the solution of this Ibdp is this term here. You just add them together, and that is the solution of the original problem. So you can always break it down like that when the PDE is linear. If you think of all the terms that you have in the PDE, boundary conditions, initial conditions, I know this is going to sound weird, but it works. You think of all of those terms as sprinkles, say, and you're sprinkling them among different problems, then you can solve those problems and have solutions together. So you also think of it as spreading the pain out. So each individual problem is less painful than the original. But you can also say, all right, the total amount of pain is the same. And you don't have to solve it that way, but certainly something that you can Here's another way of decomposing a given Ibdp into simpler problems. Again, using the same principle that's called superposition that applies to linear PDEs. So as an example, here we have a general non-homogeneous heat equation of some source term f of xt. And then we have homogeneous boundary conditions and initial conditions. So the main idea is this. If you take the source term, f of xt, and write it this way, in terms of a finite Fourier sine transform, and I say sine transform because of the boundary conditions, otherwise I might use cosine. So now, the source term is broken down into these terms. So, you could solve this problem by solving a one-parameter family of problems that have this same form, except instead of having all of little f of xt, you can take on just one of these terms at a time. So now you're solving these problems. So instead of u, I have u sub n. U sub n is the solution of this Ibdp, where the initial and boundary conditions are the same, because they were 0 to begin with, and the source term is just one of the terms of the original. So again, we want to use the sprinkles metaphor. If you think of f of xt as a sum of sprinkles, and I'm taking just one of those sprinkles and giving it to each one of these problems. Because suppose some of these fn of t were 0. Well, the initial boundary conditions are also 0. That means un would be 0. So then you can focus on the values of little n for which capital Fn is non-zero. And it turns out that, as saying here, we assume that each one of these solutions has a form un of xt is a time-dependent coefficient times sine n pi x. Now, so what would happen is, if you take this form for little un and substitute it into this PDE, what you would find is that every term in the PDE has a factor of sine n pi x. So you cancel them. This ODE is what comes out. And here are the initial conditions that come from the fact that this initial condition is 0. And then the coefficients of your source term, little f of xt, show up here as a source term in the ODE. Now, before I go on, I want to justify making this assumption. So if I assume that un of xt, because this form seems rather restrictive. If I made it a sum, m equals 1 to infinity of capital U mn of t sine m pi x. And you substituted that into this problem. Then what you'd find is that u mn of t turns out to be 0. That's what for m not equal to n. So in other words, yeah, I could assume a form like this. That's more comprehensive. But the only term in here that would matter is when m is equal to n. So I might as well just go with this. It's the only way I'm going to get something that's non-zero anyway. What makes this assumption work the source term is a scalar multiple of sine n pi x. And it's also because the initial data is 0. So those are key factors that make this statement true. So now, if you go ahead and solve these ODEs, because the initial condition is 0, this is our solution. And this comes from a solution formula for this kind of ODE that I gave you way back in lesson 9. It comes from using an integrating factor on this ODE. Now I multiply that by sine n pi x. And I sum them up from n equals 1 to infinity. And here's my solution, u of xt. My original problem. Any questions about how this was obtained? All I did was take the original problem, decompose it into a collection of problems where each of those smaller problems had a source term that was one term of the original. All other aspects of a problem were the same. Solve those individual problems, add the solutions up, which is what happened here. So this is like superposition on steroids. In the previous discussion up here, I took this problem and just broke it down into 2. Here, given this problem, I broke it down into infinitely many. But each one of those infinitely many problems had a much simpler source term to work with. So when you're solving a problem like this using eigenfunction expansion, you could think of it as performing superposition every time you do that. You don't have to explicitly think of it that way, but that is one perspective. To show you that this solution actually does satisfy the original PDE. So I need to compute UT and UXX. So for UT, I need to take a time derivative of this whole thing. Now, you might see I've written it a little differently than before. Before I had it written like this, but I took the exponential involving t, so e to the minus n pi squared t, and I pulled it outside the integral. And the reason I did that was to make this differentiation easier. So to differentiate this whole thing in square brackets, I have this exponential that depends on t times this integral that has t as a limit right here. I need to use the product rule. So when I use the product rule, first I take the derivative of this with respect to t, which introduces this factor of minus n pi squared. And then everything else here stays the same. Then, for the other half of a product rule, I need to take a derivative of this integral with respect to t. By fundamental theorem of calculus, when you take a derivative of an integral, what you're doing is you're substituting the limit into the integrand. So I'm going to get e to the n pi squared t fn of t. But this exponential, when I plug in t for s, this exponential, t plugged in for s, will cancel with this exponential that's just sitting there, leaving me with fn of t. So the product rule applied to this, with the fundamental theorem of calculus taking care of differentiating the integral, gives me all this. But this is the original source term, little f of xt. This is a finite Fourier sine transform of it. So I can just write it as f of xt. And then the rest of this, I left the same. Because now, if I take the derivative with respect, really the derivative of all this with respect to x, well, the only part where x comes into play is right here. Take a second derivative of sine n pi x, and I'm going to get minus n pi squared sine n pi x. So we get that here. This part remains the same. And look what we have. ut really is equal to uxx plus little f of xt. So the PDE is satisfied. Because we have sine n pi x, I plug in the boundary values, x equals 0, x equals 1. I will get 0. And if I plug in t equals 0, I'll be integrating from 0 to 0, so the whole thing will be 0, as it should be. Any questions on the verification of this? Or any homework questions? We have just under 10 minutes for that. Watch it almost happening with the. Okay. It's a little bit of time before. Well, okay. Today's 28. In a little more than 2 weeks is test 2. Okay. There's a couple more lessons to cover on nonlinear or first order equations. And then I'll be reviewing that test too. So sometime this week, I will put out a practice test for that. we're done.